Yes, so first, thank you to the organisers for the opportunity to share this work. So today I'm going to be talking about heat transport statistics in driven systems hosting topological phases. And in particular, I'll focus on the example of a Majorana Braiding Protocol. So this is work I've done with my supervisor at Lancaster University, Alessandro Romito, and also Ganit Maidan at Ben Gurion University. Sorry. Okay. So yeah, just as an overview, so I'm going to start with an introduction into Majorana zero mode, so what they are and where we might find them in physical systems. And then I'll briefly outline our system of interest, Majorana Braiding Protocol, and how we can model transport and scattering that's driven by this process. And then I'll analyze the heat transport statistics of this protected driven system. So starting with Majorana zero modes, so these are zero energy excitations that are predicted to exist at the ends of one-dimensional spinless superconducting nanowires. So we can see how these emerge if we consider a toy model, so a Kitaev chain. So this consists of a one-dimensional chain of n fermionic sites, and this is described by the Hamiltonian we have here. So we have some on-site coupling term, some nearest neighbor coupling, and also p-wave superconducting pairing term. So we can see how zero modes arise in the system by defining two Majorana operators, two for each fermionic site. So these are just the real and imaginary parts of our fermionic operators. And these have the property that they are their own antiparticles. So if we rewrite a Hamiltonian using these Majorana operators, okay, sorry, yeah. Our Hamiltonian now takes this form here. So, and in this form, we can easily study two limiting cases of this system. So first, a case where we set the on-site potential to be finite and set delta and t to zero. So in this case, we would have this system here where we only have coupling between Majoranas on the same fermionic site. So this is our trivial phase where the ground state of the system is just when all these sites are unoccupied. If instead we set the on-site potential to zero and let t and delta be finite, then we have the situation here where we have coupling only between Majoranas on adjacent fermionic sites. And this leaves us with two unpaired Majoranas at the ends of the chain. Now, since these unpaired Majoranas don't appear in a Hamiltonian, they define two zero energy states in our system. So if we look at the energy spectrum of such a system, it would look something like this. So this would be symmetric about zero energy. It would be a gap system, and we now have these two degenerate energy states that are given by the unpaired Majoranas at the end of the chain. So this is easy to see in the case where we set the on-site potential to zero. But what happens when we make this also finite? So what we find is, since the system is gapped and symmetric, these zero modes persist as we increase the on-site potential. And they also remain localized at the ends of our chain. So they decay exponentially into the bulk. So this is interesting because we can define a non-local fermionic state using these two spatially separated zero modes that in principle could be used to encode information as a qubit system. And since this energy state is defined non-locally, this would be protected against local perturbations to the system. So we can see how zero modes arise in this toy model, but how could we achieve this in practice? So you can show that in principle, we could mimic the behavior of the Kitaev chain if we had a system where we have a one-dimensional semiconducting nanowire with strong spin-orbit coupling. And if this is proximity coupled to an S-wave superconductor and in the presence of a strong magnetic field, then we would have a system that should admit these zero modes. So one thing that makes these zero modes particularly interesting is the fact that they are anyons, and so they obey non-abelian statistics under exchange. So if we consider the case where we interchanged the position of two of these Majoranas, this would result in a non-trivial rotation of the ground state of our system, rather than just the accumulation of some phase factor. And the form of this rotation would also be protected by the symmetry of the system. So since unitary operations such as this form the building blocks of quantum computation, this makes Majoranas appealing candidates for use in a topologically protected quantum computer. And there have been many attempts to realize them experimentally, some of which are listed here, and some of these have shown promising signs of the existence of Majoranas, although there is still some debate around some of these results. So such experiments will be focused on detecting the transport signatures of these zero modes. So we can imagine coupling our topological superconductor to some external metal lead, and then the presence of a zero mode at the end of the chain would influence the scattering properties of electrons in the lead. So in particular, we would expect to see Andreev reflection events via the zero mode that will result in a quantized conductance peak at zero voltage bias that should be robust against perturbations to our system. So we can then go one step further and ask what would the transport signatures be associated with manipulations of these zero modes, such as a Majorana braiding. So just to quickly outline the setup for a Majorana braiding protocol. So we now have 3 of these superconducting nanowires, and they each host zero modes at the ends, and we arrange these in a Y junction, as shown here. So due to the coupling between the Majoranas at the center of the system, you can show that you can, the ground state of this Y junction is spanned by just 4 Majorana operators. So the 3 external ones and then 1 in the center, gamma 0. And we couple this system to 2 external leads in order to probe the transport. So if we can control the couplings between the 3 external Majoranas and the 1 in the center with some strength delta, we can write down our Hamiltonian for the Y junction in this form here. And if we parameterize these couplings in terms of 2 angles, theta and phi, we can represent the state of our system as any point on the surface of a sphere. And if we drive these couplings, this will be represented by contours on this sphere, as we can see here. We can also define 3 Majoranas in this spherical coordinate basis, so gamma r, gamma theta, and gamma phi. And if you write the Hamiltonian in terms of these new coordinates, we see that gamma 0 is only ever coupled to gamma r, and the ground state of our system is always twofold degenerate and spanned by gamma theta and gamma phi. So if we go ahead and perform the following sequence of couplings, so first to gamma z, then gamma x, gamma y, and back to gamma z, you can show that this results in the braiding of the Majoranas gamma x and gamma y. And this is represented by the colored contour on the sphere. Now, since the form of the braiding operation is topologically protected, this contour on the sphere also shares this protection against local perturbations to the system, and also any fluctuations in the nature of the driving of the couplings delta. So we can ask if this protection is reflected in the transport quantities that are induced by performing this braiding. So in order to calculate these transport processes, we can use a scattering matrix approach. So if we have some general system coupled to 2 external leads, and we drive this system using 2 parameters x1 and x2 in some periodic cycle, we can write down the relationship between the ingoing operators A and outgoing operators phi in each of the leads using a scattering matrix S, and this depends on 2 different energies since we are driving the system. So if we can find the form of our scattering matrix, we can go ahead and write down the charge and energy currents that flow through the system as we perform the driving. So this is just given by the difference between the outgoing and ingoing distribution functions, where in the case of energy current, we weight this by a factor of energy. And the the value of these distribution functions is simply given by the expectation values of the ingoing and outgoing operators in the external leads. So in general, it's difficult to calculate the full form of a scattering matrix that depends on two energies when we perform the driving. So we use the approximation that our driving is adiabatic, so that the driving period is large compared to the scattering time. And in this case, we can approximate the scattering matrix using a instantaneous frozen scattering matrix that only depends on one energy and depends on time parametrically through the parameters x1 and x2. So if we also consider the case when our driving amplitude is weak, then we can approximate the scattering matrix in this form here, where we have three terms. So the first term governing elastic scattering events at the same energy, and then also two additional terms that allow for scattering between the nearest energy sidebands, plus or minus omega. And using this, we can write down our outgoing scattering state as a sum of these three terms. So if we go ahead and do these calculations for the case of our braiding protocol, so in the case where we have no temperature or chemical potential gradient between the external leads, we first find that the charge that's pumped between the external leads is exactly zero, and this is due to the particle hole symmetry in the system. But we do find that we have a finite pumped heat current, which takes the form here. So if we focus on the factor of Q0 that contains all the information about the driving and the braiding system, we find that this takes a geometric form. So this can be written as just an integral over the area traversed in parameter space as we perform the braiding. So this doesn't depend upon the nature of the driving or the frequency, only upon the shape of this contour. And in the case of a braiding protocol, we know that this contour is topologically protected against fluctuations to the system. So this factor Q0 also shares this protection. So we can visualize this if we parameterize our scattering matrix in this form here, and then we look at the path taken by this phase factor as we drive the system and perform the braiding. So what you can show is that Q0 is exactly equal to the solid angle that is traced out as we by the path of this phase factor on the surface of the sphere. And in the low temperature, low energy limit, this path tends exactly to the solid line, so exactly 1/4 of the sphere. So what we can show is that the heat that's pumped in this low energy limit tends exactly to some universal factor that becomes independent of the coupling to the external leads and the nature of the driving. So if we plot our heat that's pumped against temperature, we see that in the low temperature limit, we see this tends towards this universal factor of 1/4, independent of the coupling to the external leads. We also find that the heat in the two leads is anti-correlated, and this is a signature of the fact that we are pumping via a fermionic state that's defined non-locally by our two zero energy Majorana states. So if we want to go beyond looking at the influence of geometric contributions to average pumped quantities, we can look at the full counting statistics for our transport process. So this is done in practice by calculating the characteristic function for the transport chi q, which is defined as the inverse Fourier transform of the probability distribution for pumping some quantity q in some time tau. So from this, we can obtain a cumulant generating function, which via its derivatives gives us access to not only the average pumped quantities, but also the higher order cumulants of the transport, such as the noise. So if we want to do this using a scattering matrix approach, we would need to calculate this expectation value here, where the ingoing and outgoing heat operators Q are given by these expressions here in terms of the ingoing and outgoing creation and annihilation operators in the external leads, which are related by our scattering matrix. So if we can calculate the probability distribution, we can go ahead and look at the behavior of fluctuation theorems for our transport. So in the case of a static system where we have some temperature gradient between the leads, we would expect that the probability distribution should satisfy the fluctuation theorem given here. So this basically tells us that heat transfer against a thermal gradient, the probability decays exponentially with the strength of the thermal gradient. And this corresponds to the symmetry in the characteristic function shown here. So if we consider a case for our Y junction in the when we don't perform the braiding and we just have a static system, we indeed see that this fluctuation theorem holds. So the gradient of this line of the ratio of P and minus Q is given exactly by the temperature gradient between the leads. However, if we consider the case of a periodically driven system, it's been shown that geometric contributions to the full counting statistics do not satisfy the symmetry enforced by this fluctuation theorem. So there's a few examples of works on this listed here. So it's interesting to see if these geometric terms appear in the example of our Braiding protocol. So when we calculate a generating function, we do indeed find this is made of two distinct contributions. So one dynamical contribution that survives in the static limit, and also a geometric contribution that depends only upon the path that we traverse in parameter space and is hence topologically protected. So in the case where we have no temperature gradient between our external leads, the fluctuation theorem tells us that our characteristic function should be symmetric. However, when we do this calculation, when we perform our braiding protocol, we see that this is not the case, and we can see this from the fact the probability distribution is shifted away from Q equals 0. So we can go ahead and quantify the value of this correction to the symmetry by looking at chi of lambda minus chi of minus lambda. And we see that this indeed arises from the geometric contribution to our characteristic function, that in the case of a Majorana Braiding Protocol is shares the topological protection of the contour traversed in parameter space. So just to conclude, so I've shown that a Majorana braiding results in a pumped heat that is geometric in nature and reflects the topological protection of the braiding protocol. And also that these geometric contributions that we see are also evident in full counting statistics and result in additional terms to the Galotti-Cohen type fluctuation theorem. So thank you for your attention, and I'm happy to try and answer any questions.
Well, thanks a lot for the nice talk. So do we have questions? So the chat, don't have anything in the chat. So maybe to begin with, I mean, maybe it's a naive thing, but just looking at this, at the fact that you have what you have said, that this average heat transferred is not dependent on the particular driving that you do when you do the braiding protocol. Is there any underlying assumption of this? Is it completely irrelevant, or do you assume that you do things slowly, or is there any heating assumption somewhere, or is it truly completely independent of the driving?
Yeah, so yeah, you'd assume that you drive the system adiabatically. So it has to be slow. Okay. And this is assuming that you can keep the coupling of between the external Majorana that's turned off in that part of the cycle exactly 0. So there will be some error in this protection. So there is some exponentially decaying coupling between the two Majoranas, but yeah. So in the case, but this depends on the size of the system. So it's exponentially small, but there is some small error there.
Okay.